Duca ce ajutor?
Um second.
Vă ajută să ducă.
Duca, ok.
Duca.
Ok. So our topic is digital inline holography. Here we have the introduction about the holography. We have mentioned about Dennis Gaber, who was the father of the digital inline holography. Holography is a technique which consists in three parts: computation, encoding, and reconstruction. Computation of the virtual scattered wavefront, encoding the wavefront data, preparing it for display, and reconstruction, transport the interface pattern into a coherent light beam. In digital holography, the recording of the image, it is used in a digital camera, and reconstruction is done numerically using a computer. There are some types of digital holography. We have mentioned four of them. We have Fourier transformation, image plane, phase shifting, and off-axis Fresnel. The Fourier uses lenses to reconstruct the waves in magnitude and phase. Just a second. It reconstructs the waves in magnitude and phase. We have phase shifting image, which is a unique for digital holographic microscopic and gives quantifiable information about optical distance followed by light through a given system. We have also off-axis, which allows retrieving amplitude and the phase by measuring only one image with a digital camera. Computer-generated holography. Here is a brief summary for computer-generated holography. It's a method of producing holographic pattern digitally. Serves in different types of fields, from modulation of a design or a sketch to videos, gaming or TV programs. It uses Fourier transformation to stimulate the propagation of each plane of the object to the hologram plane. Reconstruction is achieved by using lenses. Here is a picture of the Fourier transformation. As we can see here, we have at the plane 2, we have a lens, which there are some waves that goes from the left to the right, and the lenses reconstruct them in magnitude and phase. Here is a small animation where displayed objects that become focused at different distance. Here, this is also using the Fourier transformation. This is like a small video. Digital inline holography, which is also our main topic. We have a description here. It is a technology which gets a 3D image with micrometer resolutions. Hologram means a complicated interference pattern where we get information about shape and structure. The first step is that the hologram must be recorded, and the second step is that reconstruction yield must yield an image of the object. And digital inline holography gets a 3D image from 2D hologram by reconstructing using Kirchhoff's Helmholtz transform. Here we have the recording process. In the figure, we have a laser, a pinhole from which a spherical wave emanates. We have an object O, which is at the right of the pinhole, at a distance d from the pinhole. We also have a screen, which in this case is at the right, which is denoted with C, it is a camera which collects all the signals and produces with them holographic picture. The procedure from which is obtained the trajectory of an object in a tank. Using a camera, we record a sequence of holograms and send it to the computer. By eliminating consecutive hologram pairs, we can generate new holograms in order to eliminate the unwanted background effects. We sum up the result picture together in a file, and we can reconstruct the file using Kirchhoff-Helmholtz transform in order to get image at different distant place in the sample volume. We have a picture for this one. As we can see at the top right, we have a laser. The laser hits the beam splitter and the mirror. The beam splitter hits the object from the side and the mirror hits the object from behind. So in this way, the object is created in a 3D and a 3D in a camera, or as we can see here, a camera or a film, and from there is sent to the computer where we can see the holographic picture. We have a quick sum up. Digital inline holography is used to capture 3D images at micron level using 2D holograms, widely used in biological experiments. Digital inline holography microscope is simple. It requires a laser, a pinhole, and a camera. We can obtain optimal resolutions. It is fast, simple for preparing a sample, especially for biological samples. And we have also a short video. This was our project. If you have any questions, please do not hesitate to ask us.
Okay, digital line holography. Now, one thing I want to note is that, let me ask Marin. Is Marin with you?
Yes.
Marin,
Yes.
what is the laser wavelength that can be used in digital inline holography?
Sorry, Professor, I didn't get that.
In the comment section, I've written down some questions. What is the laser wavelength? That's the first one.
What is the laser wavelength?
Wavelength.
Yeah, wavelength. From the laser wavelength is from the pinhole.
How many nanometer? How many?
Oh, I don't know that.
Okay. Next question is, how big could the size of the pinhole? What is the size of pinhole?
It is very small, but we did. I think that there were no explanation about that one.
Okay,
I didn't find any information about the size of the pinhole.
1 to 5.
Okay. But you need to include you need to include these values in your final report. You'll have some time to improve a little further this one, at least the Word document. Okay. So you need to include those. And I included also a link here, which you can use it as a reference to see how the digital inline holography is obtained. Okay. And no, you need to answer those. No, it's not rhetorical questions. You need to answer these, including your report. And yeah. So
we have some equations in the Word part, Professor, not in the PowerPoint part.
Okay. Then I would strongly suggest to anyone that we'll prepare the slide. First of all, is include slide numbers on all of your slides, okay? Because if I have any question, I can say that go to slide 17 and this, because otherwise we cannot make a reference. So even when we make other slides for other courses, include the slide numbers, and also include more equations also in the
Word.
in the PowerPoint, okay? In your presentation, in the PowerPoint, include the equations, okay? And let me ask Greedy. Greedy,
Yes. Yes.
can you show to us in the slides any wave equation, any propagating wave equation?
Equation
Yes.
in the PowerPoint.
Yes, yes.
I don't think we included any.
Marine, can you point us?
We have included only the plane wave phase, which is here, about the Fourier transformation. We did about PowerPoint, we did like a brief summary. We tried to make it as simple as possible.
We have explained in the Word part.
The part of equations we will put more in the Word.
Okay, okay, good. That's fine.
And the information about this topic was so small, we couldn't find any information like explained very well in detail.
Okay. But then I can, as I said, actually, I strongly suggest you check the codes on this thing that I've shared with you. Okay.
And in that one that you sent us in the link, Google Scholar, they needed to us to pay for to see those slides for digital inline holography.
Okay. I don't remember. Did it include slides or was it publications?
Excuse me?
Were the link that I sent you from Google Scholar, what was it?
Yes, to check in Google Scholar. I don't remember exactly 2 days ago or 3 days ago you sent it to us. We checked there for digital inline holography, and the information that were given needed subscription.
Okay. Now, let me add another final comment, is that have you told in the Word document, in the detailed document, have you mentioned anything regarding the digital inline holography microscopes?
Yes.
You talked about. So what is the principle of microscopes using digital inline holography?
Just a second, Professor.
Your Word document, you can open it up and you can show it to us.
I have it in the next PC. So should I read it?
No, actually, regarding the microscope, let me ask Marine. Marine, how does the digital inline holography microscope work?
Yeah, the technology is to get a 3D image with a micrometer resolution.
Okay.
Yeah, it's essential. It's essential technology for research of different biological experiments. A technique was invented in order to allow the research on moving objects, like hologram, like the one we see in the last slide of the PowerPoint with the video. This is achieved by providing image of the object's 3D trajectories.
Okay.
Do I need to add more, maybe?
Another thing that I can say, well, it's true. It can be used for 3D images, but it's also used for two-dimensional images. Okay.
Yeah, we can get the 3D image of the objects from the 2D hologram by reconstructing the cave.
Okay. And
Yeah,
then,
at a different distance, of course.
okay. Then another thing is that
Yeah.
what I can say. What
Yeah,
about
okay.
Okay. No.
the schematics of this nice? You don't have it with you, okay? I would like, if you had it, I would like you to show to all the class so that they can see it, okay? How does digital inline holography components, how they look like?
Yeah, the formula or the.
No, no, I wish you had shown to the class the sketch.
Yes, just a sec.
Свежий microscope еще digital inline holography.
Microscope.
We don't have it here in
Okay,
the PowerPoint, Professor,
okay.
because we thought that we had a limited time to explain the projects. That's why we didn't make it.
Can you go to slide 8? Can you go to slide 8?
Yes.
Okay. So this is. So you can adjust. You can simply not. You can add some more, one more component to this image, and this is your microscope. Okay. The microscope looks like this. There is a laser. There is a pinhole. There is a sample in between, and you have the screen at point C. Okay. This is it. This is the microscope. Okay. So try to include a sketch which includes laser, pinhole, and right where you have your mouse. You see where you have your mouse? Stay close to the screen. See. There, you put a piece of glass. That piece of glass is called the microscope slide. Okay. On this piece of glass, biologists, they put, for example, blood samples. If they want to see the microscopic image of blood samples, they put a drop of blood on a piece of glass and they put it right in front of that screen. Okay. In any distance from 2 to 5 millimeters. Okay, this is how far you can stay from the screen, which is denoted with letter C. So please include the schematics of this microscope in your final Word document. Okay.
Okay, we will.
Okay. Thank you for your presentation. We can continue with the next group.
We was a little emotion.
Say it again.
I was a little emotion. We all are in the presentation.
Let me see how emotional you are. Can you open the camera?
Yes,
Of
Professor.
course.
And to see all three of you drinking
There's
coffee.
light here.
Okay.
Because the window is behind us, and that's why.
Oh, I get it. Okay. Okay. Thanks again for your presentation.
Thank you, Professor.
Thank you for the time.
But you know what? Can you improve this slide? Improve this one, and include the equations and the microscope schematics. Okay.
Of course.
Okay, Professor.
Of course.
Okay.
Okay. Let's continue with the next group.
Thank you.
Thank you.
Thanks again.
Professor, if I may talk,
Yes, you can. Yes, Gray.
can me and Andy continue with the next presentation?
Sure. Yes, please.
Okay. So Andy is going to do the presentation, and we're going to do the talking part, each slide by each.
Okay.
Should I share my screen?
Yes, you can start.
Can you see the screen now?
Yes, we do.
First of all, this is our topic of project, which is called photonics.
Photonics is a word that came from the Greeks, which means light. Basically, the photonics is a field where we do research on light and use the light to perform different functions. For example, we can use the light to see. We can use the light to create, to manipulate, and for detection.
The necessity of the photonics. We are at the just beginning of the usage of photonics. Photonics devices are starting to become more omnipresent on our daily life, but usually they go under the radar. Photonics represent an opportunity which is increasing day by day with regards to the design and the manufacture of different devices. systems and integrated circuits, advanced sensing, etc.
While going through materials for photonics, I saw that it was divided in multiple types of use depending of what we need them. And I noticed that the three most important groups were silicon photonics, the topological photonics, and the microwave photonics. This photo shows how the silicon photonics is divided in four major categories depending on how we need them to be built.
Silicon photonics. When it comes to silicon photonics, we can consider it as a major force in the electronic industry. The need for data is it in continuous increase, with a wide range of applications, making this a necessity, from the daily use of the social media and different streaming media to medicine. The explosive data growth is placing demands on networks, requiring a high-speed connectivity over a long distance. This was used to be done by a large number of optical transceivers with convert electrical data into optic signals. Uh, there, these signals can be transmitted from hundreds of meters to several kilometers. But these products were really expensive to build, and with a great demand, there was not enough product to satisfy the needs for companies. The integration on optical transceivers and silicon manufacture has created a hybrid silicon laser. The base of this device is the conversion of the silicon-based electrical signal into the light, enabling data to be transmitted into a greater distance.
While searching for silicon, one of the papers sent directed me to the Intel page, which is now the major company which builds silicon, which uses silicon photonics. There is a video of 2 minutes. If you want, we can show it, or I can summarize it shortly, if there is need.
You can show it fast. You can pass it fast if it's too long.
Okay. So it basically shows that 90% of the world data was created during the last 2 years alone. So there is a need for more data.
Last 2 years, 2018, 2020?
I think it was 2016, 2018, if I'm not mistaken, because it was older report.
Mm-hmm.
So there was more need to create that to transmit data fast. So we usually until that day it was done by building great network centers, which were as large as four football fields. It says on this video. Basically, what we used to do until today was we used optical transceivers, which took data from numbers and which took optical data and sent it to from numbers, but it was only for a short distance. It was only for short distances, and also it was not how can I say? It was not company friendly because it was very expensive to create, and the demand was very high, but the supply was very low. So Intel, which is silicon, it managed to create silicon photonics, which basically their idea was that they can use the silicon data. Wait a second. The base for this was the integration of optical transceivers and silicon manufacturers that created this. The base for this device is the conversion of silicon-based electric signals into light, so that we can enable data to be transmitted into greater distances, and also it was less expensive to create. Also, with the creation of the 5G network, this can be easily implemented into the 5G.
Topological photonics. Topological photonics is also increasing exponentially in use in recent years with the development in technology. The application of technology is creating new opportunities through photonics. This part of industry drew interest from nature and the topological insulators, sorry, which transport electrons without dispersion. Frequency wave creators, polarization, and phase can be used to describe a photonic system. With a topology, we can identify a property of a photonic material that characterize the quantized global behavior of the wave function on its entire dispersion band.
Great. I have a question. Do you have any wave equation in the slides in the PowerPoint?
Professor,
We have continue on the
uh, the there were not very much information regarding the equations for the photonics, because if I search the equation for photonics, it directed me to the common lenses and things like that, which was not really part of our project. And also, I searched different papers in the IEEE.com. I managed to open them using Sci-Hub, and most of them had the equations at the later pages of the research, and I didn't know how to connect from the major thing of photonics to the most detailed thing, so I could include for formulas and things like that. That's why there are little
Okay.
formulas.
Ante, what is the unit of frequency?
Hertz.
What is the unit of wave vector?
It was wave meter for no.
What was the unit?
Isn't it meter for no? I forgot.
Ante?
Volt for meter. Sorry.
No. The volt per meter should be potential divided by meter, so this is electric field, what you're talking about. But no, Andy or Gray, so I don't know which one. Any other opinion?
Can you repeat the question, the last question once again, Professor?
What is the unit of wave vector? What is the unit? With what unit do you measure it or do you report it?
Radian multiplied by meters -1 in the exponential, or no?
That is correct. It's inverse meters. You can say inverse
Yes.
meters. Okay.
Inverse meters.
That's enough. See, the frequency is inverse seconds. Okay. Frequency is inverse seconds. The wave number or wave vectors is inverse meters. Meter to the power -1 is, you can say it so. Okay. So we're saying that and the phase. Okay. Okay, let's move to the, what is this slide? I'm trying to read this one. This is ordinary waveguide. It says that.
Yes, I can explain it to you if you.
Okay, of course. Go ahead.
This is the topological phase transition. There are 6 objects of different geometers can be grouped into 3 pairs of topology, which is seen in the picture. Each pair has the same topological invariant known as its genus. 2 waveguides formed by mirrors of the different and same topologies. Also, frequency bands of different topology cannot transition into each other without closing the frequency gap. A technological phase transition takes place on the right but not on the left. Interfacial states have different connectivity with the bulk bands, depending on the bands topological of the bulk mirrors. This is.
What is gapless? What is the line on the bottom? What is delta C is equal to 0?
Okay. Here, A is the period of the white guide propagating along Y. And delta C is the change of churn number between corresponding bulk bands on the right and left waveguides. The magnitude of delta C equals the number of gapless interfacial modes, and the sign of delta C indicates the direction of the propagation.
Okay, go to the next slide.
So the third major part of photonics was the microwave photonics. Microwave photonics has started to become more and more used in the recent years because it takes input signals and goes through the optical processing, which then gives us the output signal. It has become a major part of the electronics industry because it integration with with integrated circuits, so we can create integrated microwave photonics.
Okay.
So integrated MWP. A key entity in integrated MWP are material platforms. Many things depend on this, such as range of functionality, performance, and the size of the devices and systems. In its beginnings, it was mainly composed of lithium and silica. But this is the recent development. In the last 10 years, it has been based in three main components: indium phosphide, silicon on insulator, and silicon nitride.
Wait a second, Gray. In the report, I want you to write the chemical formulas like the indium, IN, phosphate. What is
Okay, we can do that.
that?
We can do that.
And also, you can write what does MWP mean?
It is microwave photonics, but since you
Yes.
mentioned it before, I thought we can shorten it.
This is the comparison between three major components of integrated microwave photonics. And the picture shows, for example, the reflective index. Silicon on insulator is 35, in silicon nitride is 21, and in indium, I can't read it.
So silicon, is it 21 or 2.1?
Wait a second, because I can't read it actually. It's in silicon on insulator is 3.5, in silicon nitride is 2.1, and indium phosphide is 3.1. Sorry.
Because you said 31 and 21, I guess. Am I right?
Yes.
Or?
Yes, you are right.
Okay,
My mistake.
So let's you have also the loss, nonlinear index, 2 photon absorption, centimeters. Okay. Detector. Laser power, fiber origin. Optical amplification. Okay, you can continue.
If we search, if we see the term photonics, we can think that it is something that is really complicated and we can't use it like in our daily life. But to be honest, photonics is part of our everyday life. As you can see, photonics is the major part when we try to build LEDs, which are light emitting diodes, or LEDs, which are used for lighting nowadays. Also, we can use photonics in like printers, in medicine, and it can be also used for optical pumping, and especially nowadays, it has helped also mostly in the medicine part of society.
Photonics is a key enabler for enhancing the safety and security of people, goods, and the environment. It makes possible to build contactless sensor and visual applications operating in various ranges of the light spectrum, from X-ray to terahertz, sufficiently sensitive and accurate to reliably detect potential hazards or dangerous situations. We can use it also in banks and such things. So it's harder for people to see your code as there are no prints of on the numbers.
So yeah, this was I also have done the poster, professor, because I didn't know if it was necessary for today or not. If you want to, I can show it.
You can, okay, so you're talking about photonics systems. Now, okay, that you mentioned about the photonics, the microwave photonics. But now I want to say one thing. I wrote some comments.
Yes, I'm trying to.
You can read those. So the thing was that you can, slide 2 is too long, slide 5 is too bad, slide 11 is also bad. Don't include in a PowerPoint, you yourself in the future courses where you will have to prepare a PowerPoint, and also to all the students in the class. Can you go to slide 5?
Okay.
I see no equations. You talk about microwave photonics, but what is the wavelength of the microwaves, or what is the frequency?
Yes, I found the picture. I have included the picture of the wavelengths and things in the Word document. That's why I didn't include it anymore here in the presentation.
Okay, but what is the microwave frequency?
Of what?
So when you say microwave, that wave, what is the frequency of that wave, or what is the wavelength?
I don't think I have mentioned.
The wavelength is 0.03 centimeters, I think, or no?
You think? What about the frequency?
The frequencies range between 10 in the power 9 hertz to 1000 gigahertz,
But include this
respective
in the
to
PowerPoint. Okay, so whenever you talk
wavelength.
about a system, you should list equations, first of all, wave equation, photonics. I mean, you're talking about photonics, but you have nothing related to electronics in your PowerPoint. And when I say nothing related, we want to see some information which only you understand. Okay, we took together an electromagnetic wave. So make that course visible in your PowerPoint. So you take an electromagnetic field theory. So those pieces of information, you talk about wave number, phase, polarization, but show to us a vector notation of wave propagating or something with the right-hand rule obeying, like electric field, magnetic field. Okay, so don't prepare a slide, a PowerPoint like this with no reference to the courses that only you as electronic students have taken. Okay, great?
Okay, Professor.
I listed a lot of, not a lot, a few comments on Google Classroom on how the present PowerPoint presentation can be. So I said include these equations, include these, make clear issues such as wave numbers or other important parameters.
We put words, Professor, and pictures because it's more easy for everybody to understand.
Mm-hmm.
Because
we put pictures, and then we were going to explain these pictures using words.
Okay.
It's something most of us, I don't think, has ever heard of photonics or what is photonics and things like that. So we try to do like an introduction to photonics. What is photonics? The main thing, where we can find photonics in everyday life. And to be honest, there was not formulas that were directly connected to photonics. That's why if we had to take each of the types of photonics that I found, the silicon, the topographic, and the wavelength, the microwave photonics, and we had to read like 30 pages of paper to only find like 2 pages of formula at the end of each paper. That's why I didn't know how to connect the basis of the material that I have for photonics to the most detailed things to use the formula. That's why there were little to no formulas in the presentation.
Let me see also this. I also had asked the following in the Google Classroom. So you said that these photonic components are expensive, but what is the price range? Do you have any idea of what is the price range?
For the components, no.
Yes.
We couldn't find you can't find the component. We couldn't find the price, but the price to buy the thing that Intel is putting out to buy this, that I think it's easy to find the price.
Mm-hmm.
I can try and look more in details about
I've looked about the price, but you can find the price in Google, for example. You can find it.
Okay.
Especially if you write something so specific about the photonics to find the price, but it's very difficult.
Okay, well, but if you can find them on Google, can you please report them in your Word report and say that the price range that of these components is this and that, so we can have an idea. Okay.
Yeah.
Okay, we can do that.
Okay, thank you for your presentation, and we can have the next group, which is Besmir and Rinald.
profesor.
Po,
Po se pash edhe komentet, gjithë kanë punë për të bën brapa, po si do e zgjidhim që kush e bën pas Besmirit?
po, të përshësh,
Besmiri është i mirë kuptueshëm nga që nuk ka elektricitet.
jo tani, mund ta bën, normalisht mund ta bën sipas alfabetit, sipas rendit aty. Versioni i parë është ta ndjekim sipas alfabetit. Kemi bërë deri tani vetëm Andi Mengën, e ka radhën grupi Andi Gjinit për shembull, nëse Andi është këtu. Ose pas e Besmiri ndoshta, po Joneri do të ke dëshirë ta bësh direkt po para Besmirit?
Që të mos kemi fare hatër mbetje, kam një ide. Është një faqe në Google që quhet Random Word Wheel. Edhe bëjmë kështu me llogari kujt i bie.
Normalisht
Vazhdoni koma atë bur po jepi hapi një rrugë Besmirit që s'ka pika.
Nëse nuk keni arsye shumë kështu emergjente që kam një problem,
kam për t'ikën punë edhe unë, a kupton, se gjithë për punë jemi.
Jo, unë ashtu.
Mesazhin e anës.
A ta mbarojmë të lutem ne dhe
mbaruaj ti
bëni këtë bisedë.
Besmiri ka të drejtë të vazhdojë, nëse keni shqetësime kështu, i shkruani pjesa komenteve, unë do i lexoj dhe ta shoh që mos marrin shumë kohë. Atëherë mund të vazhdojmë me Besmirin. Andi Gjinin, e kemi tu Andin apo?
Po profesor, unë këtu jam, po është Luciano në punë, edhe për nesër kam marrë leje, atë ka shkruajt aty të mesazhet.
Andi Gjini, Luciano nesër, okay. Dakor, mirë, vazhdojmë të me Besmirin.
Dakor, profesor, besoj shihet ky tabli.
Po e shikojmë, pra filmin Mikroskopi, po.
Okej, unë do të thënë jemi në grup me Rinaldin edhe do vazhdojmë në sekuencë, do të thënë njëri unë, njëri Rinaldi me prezantimin e slajdeve. Our topic is bright field microscopy. First of all, we have included this picture to show kind of what we're dealing with and what we're going to discuss. This is our topic that we're going to be focusing on right now. This is a picture or representation of what we can do using this methodology, and this is one of in the same area, but another way of representing the same thing. This is a specimen. This of 100 micrometer range, and this is called by bright field, and this by dark field.
So the way we have organized the paper and the presentation is in three main parts. We start off with microscopy principles. So microscopy in its core is based on the laws of geometrical optics, the most fundamental of which is Snell's law. So on the left side, you can see a representation of Snell's law as a series of equations. So it relates the angle of refraction to the angle of incidence. And on the right side, you have a basic representation of a linear light wave incident on a surface boundary between two isotropic media with their properties as given in the figure. In the paper, we have gone more in depth with the equation, as we have covered this topic, and we have shown how we can go from the general Maxwell's equations and the boundary conditions to the equation on the left.
So microscopy is materialized using optical lens, which refract, which their basic fundamental. So the fundamentals of which is refracting the incident wave in this case, which is light, two times, once entering and once leaving the medium. Here we represent positive lens and negative lens, and how when a wave or light, an incident wave hits the positive lens, they all the wave directions get domethënë blidhen në një pikë ndërsa e anasjellta ndodh me negative lens që në momentin që një incident wave hits the negative lens, all of the direction is diffracted. The optical lens in practice are used on binoculars, the camera lens, the microscope, or the telescope. In our case, since we're studying bright field microscopy, we will focus on microscope and we'll give some certain ideas and some a range of prices for the microscopes using bright field microscopy.
So in this slide, we have just some basic information about optical microscopes. So a microscope is an instrument that is used to produce enlarged images of small objects. And optical microscopes make use of glass lenses to magnify the specimen. So magnification can range anywhere between 300 and 2,000 times. The latter of which is for multiple compound microscopes, which use multiple lenses in succession. And these microscopes can resolve anywhere between 0.2 and 1 micrometer in length.
Okay, let me ask you something, Rinaldi, and also Besmir can answer. You said that it magnifies 2,000 times, 2000x in the previous slide?
Yeah,
So,
up to 2,000.
Okay.
There are different.
You have
there
one
is a
micrometer.
difference.
You have an object which is 1 micrometer. You multiply it by 2,000 times. How big does it become?
It is big enough for the eye of for a naked eye to see it in the when because the light go from the condenser into the objective, and then we can see them in a digital manner or by looking at the objective lens.
Okay, so 1 micrometer times 2,000 it is 2 millimeter, right?
Yeah.
2 millimeter. Then this 2 millimeter, it will go onto the camera. What is the pixel size of the camera? Do you have any idea?
No, because we more focused on the microscope. There are only use the bright field microscopy with the naked eye. So the objective, the eye goes on the objective, sees the light waves getting collected by the objective lens. So, but it depends because it depends from company to company which produce these microscopes and how they produce the digital manner on how they're going to represent this. Since because there is another thing that we will explain later that goes on to the microscopes and microscopy in general, which we have to do with contrast, sharpness, resolution, and there are some ways to adjust these components in order to get the image that is needed for a certain object.
Okay.
If we can go till the end, and then if we explain some other information, maybe it will be more clear to everyone.
Okay.
The bright field microscopy, most of the light from condenser lens enters the objective lens after interacting with object to participate in image formation, and hence we see a white background. There are certain materials used, but the one that is most important and gives a high with high efficiency are gold nanoparticles, which are used as labels in bright field microscopy. They're induced into the specimen and help because they are good because they absorb the light and they have a scattering cross section. When applied to the specimen, they look as dark spots. There is a weakness in studying thin, transparent specimens with bright field microscopy because they have a less absorption of light, and hence we need to introduce contrast methods to improve these images. Here we can see how a microscope, a bright field microscope works. If we see here, we have the light source. there is the field diagram and the condenser. The condenser and the condenser diagram, we have a thing to rotate it and to open or close the diaphragm in order for us to adjust the amount of light that we need to hit the specimen. Here is the specimen, and then here's the objective, which goes straight to camera tube if we want to see it in a digital manner, or in the observation tube if we want to see it by eye. On the left side of the slide, we have different pictures caught by a microscope that use bright field
Images.
Yeah.
So as we previously mentioned, bright field microscopy is one of the simplest forms that can be implemented in optical microscopy. It is implemented in the sense that specimens may appear a flow contrast to the background. So to ensure that the image is to ensure higher quality image, output image, there are two main factors which we can consider, which are proper illumination of the specimen and also increasing contrast through other means. So we started with illumination. The most important implementation of which is color illumination. So it is used to achieve uniform illumination of the specimen. I'll go back. Closing or opening the condenser diaphragm controls the angle of light rays that are incident on the specimen. And since the light source is not focused at the level of the specimen, the light does not suffer deterioration from dust or condenser-less imperfections. And in the next slide, we can see a basic representation of color illumination in action. On the left side, we see a cross-section of a conventional optical microscope, and the basic image path, illumination light path, and image forming path that going through each of the lenses. So you can see how the light refracts, and also we can see on the left side and the right side how setting the aperture can vastly impact illumination or the light, the spreading of light. And on the right, you can see, so basically in colors time, this light source was a tungsten halogen lamp, and so to make most out of the light produced from it and to hit the a specimen from all different directions to get a uniform illumination of the subject.
Now introduce, as I said before, obtaining the images only by bright field, the images are not clear, and there is some issues when we are looking at thin specimens, because they don't absorb as much light as the bright field microscopy needs in order for the specimen to be enough visible for the objective lens. So differences in intensity and or color create image contrast, so details are more apparent. The ability of detail to stand out against the background and other adjacent details is a measure of specimen contrast given by the formula. Contrast is equal to the intensity of the specimen minus intensity of the background over intensity of the background times 100. Producing high resolution images at high magnifications could be worthless without sufficient contrast in the image. In this graph, we show how the intensity of the background and intensity of the specimen. For the same amount of image intensity, if we have a low background intensity, we see that the contrast is very high. For the same amount of image intensity, if we have a lower background, a higher background intensity, we see that we get a high contrast. The most efficient and the appropriate one is this that all microscopes and the microscopists in this field try to achieve is this one, this linear representation here, because we don't need as much or as low contrast. We need the right amount for the image to be visible, and for all the contours and all the image components to be visible for the eye.
Okay.
Shinali?
To different contrast capabilities. So bright field is only one of the ways in which we can ensure contrast in an image, but it's very limited. So there are other ways in which we can increase contrast. So many specimens in optical microscopy, especially unstained or living material, contrast is rather poor and may be impossible to watch them in bright field contrast without enhancement or modification of the specimen of some sort. So it is common practice to reduce the condenser diaphragm below diaphragm aperture below the recommended size, or to lower the condenser substage to increase specimen contrast. But this gives up resolution and sharpness, and so it is not desirable. So many specimens absorb light fully or partially and are called amplitude objects, whilst others do not absorb any light are called phase objects, and they cannot be seen by the naked eye. So you have specific shape, density, light, internal light scattering elements, and unique chemical and structural properties such as refractive index. So we have a basic representation of different forms of contrast enhancing techniques. So on the top left corner, we see the conventional bright field approach, which this is slightly modified. It has been colored or dyed. And moving on, at B, we see phase contrast. C is DIC. D is Hoffman modulation. E is dark field, which is the complete opposite of bright field. And F is polarized light microscopy.
There is, we can see here also that for the same specimen, three different contrasts show different specifics of the specimen. The first one is the bright field one. The second one is the phase contrast one, and the third one is the Hoffman contrast one. We can see that on the bright field, as I mentioned earlier, the thin specimens are very difficult to be seen. So we use a phase contrast in order for the contours and the many details to be more approachable for the eye. And then on the Hoffman one, we do sort of as a 3D image of the specimen. Also on the other two pictures, we see different comparison of specimens in different contrasts. Modulations, and in biology, the real, for example, we have some real specimen, as in could be cells, living cells, or dyed cells, in order for them to be shown in different contrasts and different manners.
Mm-hmm. Actually, this nuclei and cytoplasm field. Ionel has a comment. He's saying, okay.
Ka comenta?
No, okay. We can read them later. But this is interesting. The figure at the bottom, nuclei and cytoplasm recognition, cells normally have two different components. The major component is the nucleus. The second component is the cytoplasm. So cytoplasm is like a wavy structure like a balloon that has a nucleus in the middle. So I'm just focused at the bottom right side monitor.
Bottom right. So this one.
Yeah, that one. Yes.
So yeah, because the cytoplasm is sort of like a gel, how do you say, material, and so biologists and microscopists use different because we mentioned earlier that these the different components on a cell have different refraction angles, and they use these Perdurando the
okay, let's go to the next slide. I just made a comment. Go to the next slide.
In conclusion, we say the optical microscopy and bright field microscopy in specific implement important concepts in wave refraction and transmission in such manner that it fulfills the need to magnify a specimen not visible to naked eye, such that studies in science can be conducted. It uses in its core the Maxwell's equation and Snell's law that is derived directly from Maxwell's equations, and color elimination in practice. To further increase the capability of microscopes, new methods, including contrast modulation, are introduced. Bright field, phase contrast, and Hoffman modulation are all means to amplify the efficiency of microscopy. In the latter slide, we show a trinocular microscope with all its specifics that are given by the company that it produced in, and a price for this microscope. It depends. So there were different specifics. It depends on if you're using a binocular or trinocular one, and the range between these microscopes is in 100 to 200 euros. So the binocular one could be like 200 euros cheaper.
Okay. This is digital microscope. PCE. Okay, thanks. Thank you for your presentation. And now, in the wave equation, what parameter in the propagation constant is bright field making use of?
So in what parameter of?
Of the wave propagation constant. I wrote it in the comment section, so to be clear and to Renat, which part of the wave propagation constant? So in the course of electromagnetic wave, I've mentioned this a few times during the course, talking or trying to note the important element of content. So how does work? You have a wave which is input, it passes through the sample, and then what do you get on the other side?
You get the refracted wave, which is so basically the fundamental is that the specimen absorbs the light, so absorbs. Okay, could be absorbing the.
Desmir, you remember attenuation constant, right?
For the imaginary or real part?
Yes.
Also the skin depth and how much it penetrates
which
the specimen.
component of the propagation constant is employed in bright field microscopy? Is it the complex part or the imaginary part?
It is the complex part because it is alpha plus j beta. So it is the attenuation constant, but also when we do the phase contrast, we make use of the phase.
Okay, think about this one, but I want this comment made in written form in the report. Okay, I'm going to answer at the end of the class. So gamma is equal to alpha plus j beta. I wrote it in the comment section. Think about this one, but I want details. Okay. Let's go to the next group. And Yonid made a good comment. He's saying the depth of field is generally created depending on two things: the lens and the sensor size. Okay. For example, a phone camera sensor is too small to generate depth of field. I don't know what this means, Yonid. Really, we can discuss this later. What does it mean to have a generated depth of field? Even if the camera lens isn't okay. The most used is
Ili është në fushën e kësaj, prandaj dim ka shkruaj informacion.
Yonidi punon në këtë fushën e optikës?
Jo në fushën e optikës, në fushën e që merret me këtë. Kam përshtypjen se nuk e di mirë, por Jonel mund ta tregoj më mirë, po e di që merret te kjo pjesa e kamerave dhe e fotove, të gjitha këtyre që ka të bëjnë me imazhet. Digitale dhe jo vetëm.
Okay, I have to read this one, the comment of Yonel in detail. Then after, wait a second. Then we have some suggestion on the union. Okay. Ismiana had a comment with Donaldi. Dorianis. Okay, so Donaldi is asking. Well, Donaldi is right after Bjorna. If Bjorna gives us permission, Bjorna Chisaraku, we can continue with Donald Baroli.
Profesor, nuk e kemi problem, ne këto që kanë punë mund t'i tolerojmë që të prezantojnë domethënë para, ose që kanë problem.
Kuptimin? Atëherë Donaldi mund të se keni shkruar komentet a është e mundur?
Vazhdojmë ne profesor.
Vazhdoni, Donaldi vazhdoni, po. You can start sharing the screen, the monitor. But again, sorry, Besmir and Rinat, more equations, please, in the PowerPoint and also in the Word document. Let's continue.
Okay, so our project is about metamaterials. In the first slide, we have a rough explanation of theoretical and mathematical views of metamaterials. Metamaterials are a combination of two words, meta and materials. Meta comes from a Greek word which means something advanced, something that goes beyond nature. Material is a Latin word that means matter. Metamaterials have arrays of sub-wavelength elements that respond to the electric and magnetic component of electromagnetic waves. They follow a left-hand rule, which is formed by the three vectors, electric field, magnetic field, and phase propagation, due to negative epsilon and mu. Negative permeability is obtained using patterns such as split ring resonators, while negative permittivity is obtained by arrays of thin wires made of aluminum, silver, and gold, etc. Properties can be described by Maxwell equations as below. First, we have the curl operator, which is the first one. The E is the electric field vector. The minus J is the imaginary number, -1 in square. The omega is the angular frequency, the mu, and the magnetic field vector. When they are in wave plane, they follow the right-hand rule. If we apply a negative epsilon and mu, they follow the left-hand rule, such as below, minus omega mu times the magnetic field vector, and the other one omega epsilon times electric field vector. These are called double negative materials because they have both negative epsilon and mu. Firstly, the double negative materials follow the sum of epsilon negative materials plus mu negative materials, and then they follow the negative index refraction. Usually in positive refraction, the wave doesn't refract, while in negative refraction, it refracts in the different, such as in the video. There's a short video.
Now, Dorian, I have a question for Dorian.
Yes, Professor.
Refraction. Have you noticed in any of the materials you have read, for what wavelength does the negative refraction process work?
A Swedish Since we talked about metamaterials, we said that negative reflection applies only on the materials that possess both negative permeability and permittivity. So there we had a little bit of demonstration of how a propagating wave reflects in the inside, let's say, term of the after it goes in the contact with the interface. So in the furthermore slides, we have talked about that. If I can continue.
Maybe
we can
ahead.
see the negative refraction in the telecom waves, the telecommunication waves.
Okay. Now, my question, when I saw the previous slide, it is strongly related to the information in this slide. So the question I asked here, can you go to the next slide? In slide 4, yes. Okay, you explained this one. Go ahead.
Okay, my part was about to talk the structure of the metamaterials, which are considered as periodic structures like antennas or waveguides or bandgap materials, etc. So a unique cell of metamaterials consists of split ring resonators and a mesh of very thin wire structures, as they are shown in the picture below. As we can see from the first picture, let's say from the point A, we have epsilon negative materials, which is related to the permittivity. It is called epsilon negative materials, combined with mu negative materials, which is related to the permeability parameter. Combined together, we have double negative metamaterials, which are about our topic. In the second picture, we have the real image of a metamaterial, which we can see we have split ring resonators placed in the electric structure combined with the electric wires. While in the second part, we have the graphs, which means that from the first one, we have to make the negative permittivity using thin wires. And we are interested only in that part of blue when the frequency is lower than the plasma frequency. In the next graph, we see that from the split ring resonators, we are interested only the red part of the graph with that frequency, and then together combined from our unit structure of metamaterials. So to make a metamaterial, there are a metamaterial consists of 10, 18, or even 20 unit cells combined together. Go to the next slide, please. Okay, how it is made, the negative permittivity. Negative permittivity is related to the electric field. For any metal below the plasma frequency, which is the frequency at which it becomes transparent, produces negative value of permittivity. This is also expressed in the equation below when the WP, it means the angular frequency of the propagating plasma over the angular frequency of the propagating wave. Metals which are used to make the negative permittivity are copper, aluminum, silver, and gold. Go to the next slide. For negative permeability, we use split ring resonators, which are a unit cell of them is made of two metal rings, which are centric, which means they share the same center. Their parameters are shown in the graph. As we can see, they are very small parameters, 850 nanometer about there. But how it functions? Firstly, we have a time-dependent electromagnetic field which penetrates through the rings, which makes induced currents which go around the ring. So the gap between the rings acts like an inductor, while the rings itself act like a conductor, so we can relate them as a LC circuit, as it's shown in the next picture. So, yeah, it's me, Dory.
Sorry, Dory. Okay, Dory. In this slide, how big are those two concentric rings. How large are they?
Their parameters are in the graph, Professor, which shows A, which is the length. It is around 850 nanometer.
That's good. Okay. So that's perfect.
And their thickness go around 30 micrometer. So they are very, very small.
They're very small. Yes, they are in the order of micrometer. Yes, that is correct. Now, Besmir, you are answering some of my questions in the comments section. So please have a look at the numbers that Dorian is presenting. Okay, he is in the 850 nanometer or 600 nanometer range. You are also to some similar range. Okay, so Besmir, can you confirm you are listening to me?
Yes.
Arinati, can you follow the communication in the chat section? Sorry, Dory, thank you for noticing this to us. You can continue.
Okay, so as the magnetic field was penetrating through the rings, we have induced currents that go around the ring, and this produces the magnetic dipole, which can be adjusted to be out of phase or in phase with the external field, leading to negative permeability. So we are interested only in that part which makes the permeability negative. So the idea is to build a strong magnetic resonance by first creating induced currents, as it is shown in the picture, and combined with the thin layers, they make both these parameters negative. So we refer them as negative index resonance parameters. Next slide.
Next slide, we have the application of metamaterials. Metamaterials have a wide range of application, which one of them are antennas. In antennas, metamaterials are used so they can have different characteristics than usual antennas. These antennas have layers of metamaterials, so they improve its performances. They can enhance the radiated power, improve parameters, and reduce the size of the antenna. The design can be in form of an unit cell, so that the parameters epsilon and mu satisfy the requirements of the resonant frequency. An antenna can radiate 95% of input radio signal at 350 megahertz. And metamaterials in experiment by scientists are small as 1/5 of a wavelength. Metamaterial can enhance the gain and reduce the return loss of a patch antenna. Next, we have an absorber. An absorber efficiently absorbs electronic radiations. Absorbers usually have a sandwich structure with certain metallic patterns. They have both free space epsilon and mu and relative mu and epsilon. Free space is the vacuum epsilon and mu. There is no transmission in the metamaterial, and metamaterials are used only for their reflective properties. Absorbers offer benefits over conventional absorbers, such as supplementary miniaturization, wider adaptability, and increased effectiveness. To create a high ratio of electronic magnetic radiation absorption, it requires effective medium design, permittivity, and magnetic permeability. The first metamaterial-based absorber utilizes 3 layers, 2 metallic layers and dielectric, and shows a simulator absorptivity of 99% at 11.48 gigahertz, as shown below. It was able to achieve an absorptivity of 88%. The difference between simulated and measured results were due to fabrication errors.
The third application of metamaterials is, as it is shown, superlenses. I've just written a small description about superlenses, as it is the main topic of other groups. So superlenses use metamaterials to go beyond the diffraction limit, and it has resolution capabilities that goes beyond ordinary microscopes. So we can use metamaterials to build lenses that are very small in parameters and which can do which can do the same, let's say, the same job way better and using very less parameters. In the second picture, it is shown how the propagating wave it is reflected, and in the internal focus, and also the same thing happens for the second part until the image it is created after that. The fourth application of metamaterials is cloaking, which can be achieved by canceling the electric or magnetic field generated by an object, or by guiding the electromagnetic wave around the object. So it means that we can transform the coordinate system in such a way that the object inside the electromagnetic field will be 0, and so it will make it disappear, or it looks invisible.
Okay.
In the last
slide, we have the last application in our PowerPoint, which is sensors. Sensors are usually stated together for strong electromagnetic properties. Usually, plasmodic metamaterials are used for sensor. Symmetric split ring resonator are separated by dielectric inserts. Metamaterials provide tools for significantly enhance the sensitivity and resolution of sensors. Metamaterials sensors are used in agriculture, biomedical, etc. In agriculture, the sensors are based on resonant materials and employ SRR to gain better sensitivity. In biomedical, wireless strain sensors are widely used. Nested SRR-based strain sensors have been developed to enhance the sensitivity.
Go to the last slide.
We have the prices of devices that use metamaterials. What we found, and we got an email from one of the biggest companies that produce metamaterials. They provided us with prices of their notch filters that use metamaterials. These are only 6 of them, but we have
like 12, but they look the same.
If you want, we can show them.
Actually, that's good. If you have in the prices or in the data sheet, do you have the absorbance as a function of the frequency?
We can show the email, but it was very restricted. It was only about the prices. They didn't give us much details about this.
They give you the data sheet. Probably they might have them on the website. Meta Optics, right? What was it, the names?
That's the email we got, but they showed us that they couldn't give us the metamaterials prices because they had only for themselves.
The prices are here, like 700. So they give the notch filters.
Yes.
So they say it's 370 millimeter by 70 millimeters. So this is 7 centimeter by 37. So it's like this much by this much. Or this is huge. Now that I'm thinking about it, it's like a piece of paper times 7 centimeters. So are they selling this half of the page A4 by a price of what is this?
$750.
They have like 375.
Very cheap. It's strange.
Because they are very thin, as we can see.
But this is cheap. I don't never expect to get a piece of this big, and this is notch filter. Okay. So notch filter. Okay. What is your understanding when you hear about notch filter?
They only let the bandwidth only in 2 frequencies, F1 or F2, between only those frequencies.
Okay. Okay. Thanks.
We also sent different emails to other people, but they didn't respond, or they say they couldn't provide us with more details.
We can show the emails, but it's not.
No, it's don't show it.
Also, we can show us our poster if it.
That's our poster.
That's how it looks.
That's good. That looks good. Okay. Okay. Thanks again. We can go to the next presentation.
Thank you.
Thank you.
Thank you.
Christina and.
The boy share, Professor?
Yes, you can.
Okay, so we have selected, in fact, to present part of the report and part of the PowerPoint, but not all of them, because the PowerPoint is more about data sheets and also figures, images.
Okay, you can.
So the title of our project is optical coatings, and we should first start by giving the exact definition of what optical coatings are, and we can say that they are an increasingly critical component of complex optical systems such as telescopes, microscopes, lenses, or cameras. And when they are properly designed and fabricated, they can be used to alter the optical properties of an optical system by increasing or decreasing the reflectance, absorptance, polarization, or transmittance. And usually they consist of one or more layers of material which are deposited upon a medium, and the performance of the whole optical system will depend on the number of layers used, the refractive indexes, and even the thickness of these layers. We can mention a very basic example. If we have an 8-lens camera, which is made by uncoated material and incoming light wave, then each glass surface will reflect approximately 4% of the wave. And if we take the cumulative wave that is reflected, we see that it results in a substantial loss of image and can cause even ghost images. Some of the key concepts that we use frequently are refractive index, reflective, and anti-reflective, but I'm not going to explain them now because we'll see them later.
Based on information that we have, we know that optical coatings are divided in 4 groups, which are beam splitter coatings, anti-reflection, high reflective, and filter coatings. Anti-reflection coatings are used to maximize the throughput and to reduce the ghost image. Ghost image means something blurry or out of focus. Beam splitter coatings are used to direct the incident light or divide the incident light into respective transmitted and reflected one. High reflective are used on the mirrors in order to maximize the reflectance, and we are going to talk about the materials that create optical coatings, which are metals, dielectrics, and semiconductors.
Okay, so much emphasis in this project is put on AR coatings or anti-reflection coatings, and we already know that if we have a wave that's propagating in air, and the moment it encounters a medium, part of it will be reflected and part of it will be transmitted. But this happens when the medium is uncoated. But if the medium is coated with an anti-reflection coating, we'll see that the purpose here is to make the reflection coefficient, or the gamma, to make it equal to 0, or to have 0 reflectance. And how this happens, if we have, we see that for the incoming wave, part of it will be reflected at the interface between the air and the coating material, and the other part will be reflected from the interface between the coating material and the medium that we have. For a very specific value of the thickness of this slab, which is usually the electric slab used for anti-reflection, which is lambda over 4, or a quarter of the wavelength, then one of the reflected waves will travel half a wavelength, lambda over 2, farther than the next reflected wave. And this will cause a destructive interference. And one of the Fresnel's equations that has to definitely be obeyed here is that the refractive index of the coating material is equal to the square root of the product of the index of the air times the index of the substrate. We'll go very quickly through this graph in case we have a glass component which is uncoated and is known as NBK7. In the case it has a refractive index of 1.52, we'll see that the reflectance will be something more than 4%. If we put a coating material with a refractive index 1.38, the reflectance will get lower, but not 0. And ideally, if we put a material with a refractive index 1.23, then for a specific wavelength, we see that the reflectance will be 0. And why this happens? This happens because 1.23 is equal to the square root of 1.52, which is the law that we have to obey. This works for single layer AR coatings, or we may also have double layer, where traditionally the first layer, which is, let's say, incident to the air, has a lower refractive index relative to the second one. And 2 equations that have to be obeyed here are N1 times D1 is equal to N2 times D2, where N1 and N2 are the refractive index of the first layer and the second layer, and their thickness. And the second equation has to be obeyed is that N1 times N2 is equal to N0 times Ns, where Ns is the index of a substrate and N0 the index of the air.
This explanation can be explained also based on formulas. Here we have evaluated the general expression of electric and magnetic field for each medium, as seen in the figure. The incident wave that comes from the medium 1 goes to medium... Sorry?
That is correct. No, that's good that you have the detailed equation. No, go ahead. I just confirmed that.
Okay.
It's okay.
The incident wave that comes from medium 1 passes the interface to the medium 2, and one part of the wave is transmitted and the other one is reflected. The same happens with the wave that goes from medium 2 to medium 3. After evaluating the expressing general expressions of electric and magnetic field, we applied boundary conditions for these fields, for zeta equal to minus d and zeta equal to 0, in order to obtain the effective refraction coefficient and transmission coefficient. Since the power in the medium 1 is equal to the power in the medium 2 because the medium 3, because the medium 2 is lossless, then we have come to this relation between transmission and the refraction coefficient. According to the knowledge that we have, if d, which is the thickness of the slab, is equal to lambda over 4, then there is no reflection, which means that the refraction coefficient is equal to 0, and the transmission coefficient achieves its maximum value.
Okay.
We also
I make a short comment. Right now, the time is over, and I may need to switch a class. A mund ta ndërpresim pak sa të ndroj klasën unë, nuk presim pak?
professor, patjetër.
Okay, kërkojnë yes. So let's end this session for a few moments. We'll restart again.